In this video, we'll use Excel to calculate various measures of variability, including the range, variance, and standard deviation for a set of scores as well as a simple frequency distribution. We'll start with a set of scores. Here are 11 observations copied from a question in Chapter 3 of the textbook. The first measure of variability we'll discuss is the range. The formula for the range is simply the highest score in a distribution minus the lowest score in a distribution. This set of scores is already sorted from highest to lowest, and so the range is simply equal to the highest value minus the lowest value, or in this case 7. The range is a very simple measure of variability, but it has one major disadvantage. If instead of a high score of 7, we had an extreme score, say 70, the range would go from 7 to 70, even though the majority of the observations did not change. This is similar to the disadvantage of the mean. That is, extreme scores, or outliers, can lead to a distorted value. One way to overcome this disadvantage is to use something called the Inter-Quartile Range, which essentially looks at the range of the middle half of a set of scores. By excluding the highest quarter of the values and the lowest quarter of the values, we eliminate the effects of outliers. Your textbook does not cover interquartile range, and so we'll move on to the next measure of variability, which is the mean deviation. Here is the formula for mean deviation. I've already calculated the mean of this set of scores using Excel's average function. So the next step is to subtract the mean from each of our individual scores. So I'll type equals the score minus the mean. So a score of 7 is 4.45 units away from the mean of 2.55. Now I want to copy this formula into the rest of my cells, but I want each formula to reference the mean cell, and so I'll enter $signs before the row and column labels for the mean. Now, if I sum these deviations, let's see what happens. As you can see, the sum is 0, which doesn't really tell us much. It's 0 because of what the mean is. The mean is the point in a distribution of scores that lies at the center. So all of the scores that are larger are offset by all of the scores that are smaller. Essentially, the problem is that half the scores are negative and half the scores are positive. So we have to determine how to get rid of the negative signs. And there are a couple of ways to do this. The first is to use the absolute value. Absolute value is a fancy way of saying eliminate the negative sign. There is actually an Excel function for absolute value, if we type in absolute, we can see that the function abs returns the absolute value of a number. As you can see, this number did not change because it was already positive. However, if we copy this into the remaining cells, you can see that now every score that previously had a negative deviation has the same size positive deviation. And so now, when we sum those scores, we get a non-zero value. This number represents the numerator of the mean deviation formula. That is, it is the sum of the absolute values of the deviation scores. The final step is to divide by our sample size, which is equals our sum of our absolute value deviations divided by our n, in this case 11. This tells us that each score is an average of 1.69 units away from the mean. There's another way, though, that we can get rid of negative signs that is much more common in statistics. That is, we can square the number. A negative times a negative is a positive, just as a positive times a positive is a positive. Regardless of whether the number is positive or negative, if we square it, our result is positive. I've created a column for squared deviations, and I'll enter the formula equals the deviation score squared. This character is the symbol above the 6. That is, we hold down the Shift key and press 6. It's called a caret, and tells Excel that we want to raise that number to the power of 2, or square it. So 4.45 squared is 19.84. We'll copy this formula to the rest of our values, and then sum those squared deviations. This is the numerator of the formula for variance. One thing that can be slightly confusing about variance is that variance is represented by s squared. We don't square anything. S squared is simply the name for variance. We'll see why in a moment. In any case, we have the numerator, which is the sum of squared deviations, and just as with the mean deviation, the final step is to divide by n, or the number of cases. So our variance equals the sum of our squared deviations divided by n. This number tells us that, on average, each score varies from the mean by 4.25 squared units. You'll recall we squared our deviations. This can be confusing when it comes to interpretation. For example, what is a squared year or a squared dollar? Because of this, we often take an additional step, which is to take the square root of the variance, which turns our units back into their original form, and this is referred to as the standard deviation. The standard deviation is the most common measure of variability presented in most academic papers. The standard deviation is represented by the letter S. This is why variance is represented by S squared, because S is the square root of the variance. So once we've calculated variance, calculating the standard deviation is very simple. The standard deviation is simply the square root of the variance. In order to calculate a square root in Excel, we can use an Excel function. SQRT is the Excel function that returns the square root of a number. So I'll select the variance. The result is 2.06. This means that, on average, an observation in this set of data deviates from the mean by 2.06 units. The mean deviation and the standard deviation have similar interpretations, but have slightly different values due to the slightly different ways that we calculate them. Before we move on to simple frequency distributions, I want to mention that there is an alternative way to calculate variance and standard deviation. Textbook refers to these as the raw score formulas. These can be a bit simpler in that they require fewer columns of calculations. The numerator in this case is simply the sum of each score squared. So I can create one column and type in equals the score squared. As you can see, the square of 7 is 49. We can copy that down to the rest. We then sum those squared scores, and then again divide by n. In this case, after we divide by n, we then subtract the squared mean. The variance equals the sum of our squared scores divided by n minus our mean squared. As you can see, this gives us the same value. If we take the square root of this number, obviously we'll get the same value for the standard deviation as well. The advantage to using the first equation, or the first set of equations, is that when we make our final calculation for the variance, we simply have to take one number and divide by another, but it also means we have to calculate two columns. The raw score formula only requires one column, but the final calculation is a bit more complex. You should try both and use whichever one you're more comfortable with. The formulas for simple frequency distributions are very similar to the formula for a set of scores. The only real difference is that they now include an f, or frequency variable. Here is a simple frequency distribution, also copied from the previous chapter of the textbook, and I've already created an f times x column in order to calculate a mean for this frequency distribution. You may think the next step is to square that product. I have an f times x column, so I should just square it. That is not correct. According to the order of operations, exponents come before multiplication. What this formula is telling us to do is to square the x's and then multiply by f. So I've created an x squared column, very similar to the previous example, and I'll simply type in equals, click on the x, a caret, and then 2, which squares my x value, and copy that into the remaining rows, and then multiply that squared score by the frequency. For comparison, let's square our f times x column. As you can see, these values are very different. If we perform calculations in the wrong order, we can end up with a very wrong answer. So again, this is not the correct way. We square our scores and then multiply by the frequency. I will now sum this column, which gives us the numerator of this expression. Next, I divide by n, and then finally subtract the squared mean. Just as before, the standard deviation is simply the square root of the variance. So I'll insert function and select the square root and click on the variance. This number tells us that on average, a score in this simple frequency distribution deviates from the mean by approximately 1.6 units. This covers calculating